Hi guys. So right now we're going to talk about polar curves. So meaning what we want to look at are functions of the form r is a function of theta. So it's just a curve, but now as we did in parametric, we now have the in polar coordinates. So what does this look like? I'm just going to do on the board the most simple possible thing. Of course, we know, say, a circle in Cartesian coordinates, x squared plus y squared equals 4 is a circle of radius 2, right? But this is just r squared. So in polar, I just write r equals 2. Super simple, right? Because everything is based on circles. So this is a much more complicated looking equation than that. So this is my pretend it looks like a circle of radius 2. Also, we could do, say, constant theta. Sometimes you'll see that, like theta equals, put it over here, theta equals pi over 3. Well, that's going to tell me r is anything, theta is pi over 3. So that's a line like this. Okay? If you want to think about a line that's not through the origin, that's not so pretty, we're not going to worry about that too much. You won't see that very often. Okay? But the real nice thing about this is, okay, see how easy the circle is? So that then maybe when we do a little more calculus with it, it'll be a little bit easier to do things that have a certain circular symmetry. Now let me show you some more interesting ones that have that kind of symmetry. It always takes me a minute. So I'm going to show you with Desmos. Right, come on, let's go. There we go. I'm going to show you with Desmos how this works. So the first thing, whoops, go away. The first thing, when you pull on Desmos, of course, it looks like this, right? You've got that Cartesian grid. If you want to change it to the polar grid, you go up here to the little wrench, pull it down, and you can change this into a polar grid. Right, come on. There we go. And you want to make sure it's in radians, because otherwise it'll all be all messed up. Okay, fine. All right, stop with that. I don't know what's going on. Okay, there we go. So there's our polar grid. And then all you need to do is put in your equation in the r theta form. Like, for example, if we want to do r equals 2 cosine theta. So we just type it as, okay, so that's the one thing. You do have to tell it that you're doing the r, because otherwise just having the grid up isn't enough. You have to tell it that you're doing the r, so then you have to put r equals, and then you have to write it cosine. And then if you write the word theta, it'll put it in automatically. And let me see, that is not very big, okay, but that is a circle as well. And it is a circle of radius a half, and it's moved over. So most of these, oh, okay, oh, I forgot to tell you this. So if you read in the book and do some of their modules, they do this weird thing where they graph it on a Cartesian with r and theta and then kind of wrap it around. I hate that. I won't do that because it just really confuses me. So if that's a method that works for you, you know, by all means go ahead and use it. But my thing is just, let's just use Desmos and have it draw it for us. Now, what happens though with this as we go around, and your calculator also, any of your graphing calculators, they all have a way of doing this. So you might find that that's easier for you to use than this, but this is what I have, so that's what I use. So look at what happens though as theta goes from 0 to pi, okay? If theta is 0, cosine of 0 is 1, so that puts us out here. Now, if theta is pi over 2, okay, I'll go so fast. So if theta is pi over 4, cosine of pi over 4 is root 2 over 2. So we have this here, so that would be like pi over 4 somehow over here, right? Pi over 3, you're going to get root 3 over 2. That's going to be sort of over here, right? This one's pi over 4. This one's pi over 4. This one's pi over 3. And then pi over 2, it's actually 0, right? Cosine of pi over 2 is 0. So it from 0 to pi over 2, it gets you this. Now, what about these negative ones? This is a weird one, right? Because cosine is going to be negative from pi over 2 to pi, right? So in fact, it's like we're going out this way and flopping back. That's why it goes underneath, because here we have for the pi over 2 to pi, we have negative values of r. So it's like it would continue over here, but because the r value is negative, it shifts it over here on the other side of pi. Okay, so this is kind of a special case. And if you look at sine also, it's very similar. It just is sitting on the top there, but this is the same thing. In 0 to pi, you start sine of 0 is 0. By the time you go to pi over 2, it's 1. And then this one, sine is, is just still going to be positive. So here you don't have it flipping over, but you just kind of keep going around. So and then both of these see r of radius 1, of radius 1/2 because of diameter 1, right? If I put something like a 2 in front here, now I have to make my thing a little bit smaller because I'm now going out 2, right? Because if I put in sine of pi over 2, r is now 2, so I'm going all the way there, okay? Whereas, like we saw before, if I put a 2 in here, then different things are going to happen, okay? So this is actually called a 4-leaved rose. Now, if you look at this, now you see it automatically, which is nice about Desmos, is it like picks the best thing. So from 0 to 2 pi, what happens when you do this rose? If I'm starting from theta equals 0, I'm here. And then at pi over 4, right, I'm going to have sine of 2 pi over 4 or sine over pi over 2. That's 1. Well, here's the pi over 4 line right there. Let me make it a little bit bigger. Okay, there we go. So there is sine of pi over 4. And then if I go to put in theta equals pi over 2, of course, I'm going to end up with sine of pi, which is, again, going to take it back to 0. So between 0 and pi over 2, that 2 makes it do that whole circle, but only within this quadrant. And then we go through and it goes again. Actually, it's kind of funny because, yeah, so it goes again and it goes again and it goes again. Okay, so that's how these go. Cosine, these are all called leaved roses. Like this, cosine goes like that because we're starting from 1, so it rotates it. If I do 4, of course, I'm going to have 8 leaves. Funny thing is, if I do 3, I'm not going to get 6 leaves. I'm only going to get 3 leaves. So that's kind of cool. And you see, if you let your calculator work this out, it's kind of funny. Again, it goes like, it actually does it like this as you go around because of the positive and the negative. And so the 4-leaved ones are similar. It goes back and forth and back and forth. It's kind of cool. So you might want to look at that if you have a calculator that can draw out the curve. So let's do something a little bit different. Those were all the roses. Now let's see what happens if I do something like this. Okay, this is actually called a cardioid. Obviously, it looks a little bit like a heart. And if you see what happens, see the source of it's different now. It's got a 1 plus or whatever, right? So if I put in theta equals 0, I'm going out to 2. Now, if I put in theta equals pi over 2, right, then cosine of pi over 2 is 0, so I'm back to 1. Now when I go around to theta equals pi, cosine of pi is -1, so that bumps it back to 0. So that's where you get that like there and then around like that. So these are whole families of curves. If I put a sine theta it looks the same as just rotated. Let me get my cosine back so that we can see it. Okay, the other thing that can happen though is, for example, let's if I put a 2 here, now this is actually called a lemniscate, but you get a loop in it, right? So you can get a loop, and the size of the loop sort of depends, or the lack of a loop. Now there's not a loop because this number is bigger than that. So it depends sort of on the ratio of these two things and stuff like that. People used to study these all the time. For our purposes, you don't have to know what it does. You can just graph it. You can get all kinds of neat stuff if you want, just by changing these things. What are we really going to do with it? We will see, we're going to do some area problems where we do an integral with the area, but what I want you to do is just be able to graph it on the calculator or on the computer and then use it in those forms. So we can do multiple. Let's say I had something like, all right, let's make it something simple. Something like this. And then we might want to graph another one. Here, come on. If I want to graph something like R equals cosine theta. Okay, that's not very interesting. Let's do R equals 2, R equals 1. Let's do R equals 1. That's easy enough. So now we can look at different areas. You can look at the area over here. You can look at the area over here. You can look at the area out here. This is kind of problem that we'll be doing in the next section. Okay. Oh, let me show you a few more fun ones. Not surprisingly, you can get, let me see, let's make it so you can get some spirals pretty nicely like that. This is R equals theta. It just did it all the way up to 12 pi. If I want it smaller, of course, I could do square root. Yeah, come on, come on. That didn't work. Oh, now it's too small. We can't see it. So we're going to zoom that in. But, you know, so you can get these different kinds of very more interesting curves. There's also, what is the sine? So like the lemniscate, I think, let me see. I think it's sine squared, well, sine squared of theta. Yeah, there you go. That's kind of a neat one too. Also, this one's a little bit of a pain to draw out because of this business with the square and the over and those whatever. So, but there's just different stuff you can do. So I guess that's all I wanted to do with that.